So thank you for the introduction, Kim. So the name of the tool is Timesecbench, after mbench, for example. So I'm going to present this benchmark suite, which is a work in collaboration with Mathieu Escoutlo at INRIA, which is a PhD student. And so I will show you the tool, what the motivation is, how it works, and why I'm presenting it here to have some feedback. Okay, what are the still missing? So the scenario is you are a hardware designer who wants to quickly look for timing leakages in your microarchitecture. So you want to verify that your design is sound, or you are a security evaluator. We want to verify the hardware soundness, and you want to verify low angling faults. We are looking for the possibility of a leakage. So we are looking for a vulnerability, not for exploitability. Meaning that sometimes there is a vulnerability that cannot be realistically exploited. And for that, we are using the now common setting of covert channels. So basically, you have an attacker that tries to establish a communication between two security domains. So the first one is a Trojan, and that tries to send information to the second security domain, which is a spy. So here, our threat model is microarchitectural leakage, meaning that we can only share information, encode information in the microarchitectural state, not the architectural state. We cannot use registers, memories, CSS to encode information. Like things like if similar to there is a clear between the Trojan sending information and the spy trying to read it. I want to give you a small example, which is not the cache one because it's too common now. How to encode information in the branch history table. So basically, this is the hardware optimization in order to optimize the speed of branches. And for that, we'll have counters that count the number of branches taken out of the last 4 branches at a given address. For example, we have a gadget with a lot of branches and a given condition, and will branch if less than to the end of the gadget. So we can first clear all the counters by choosing the condition for the not taken branch and calling the first branch. So all the branches will be called with the not taken condition. And so we will clear all the counters because we will count one not taken branch for all the addresses. Next, the Trojan can encode the information at the Y branch by just calling this branch with a taken condition. So you repeat this step 4 times, and so now you have a branch BHT counter for this address equal to 3. And now the spy can test a given counter. So it will test the counter for a given value O by selecting the corresponding branch and trying to the taken condition. If I and O are different, so basically you are taking the branch for a BHT counter assuming not taken, it will be slow. But if O is equal to I, then you are using a taken branch, assuming a taken branch. So the BHT is working properly and you have a fast branch. So with that, you can build what we call timing matrix. So you have probably seen this kind of diagrams from the work of Weiser, which is similar to that. So here, for all the Trojan values and all the spy values, you measure the timing associated. On the left, you can see a vulnerable design. You have horizontal variations, meaning that we can detect, the spy can detect when the Trojan is encoding a value, what value is encoded. On the right, you can see a secure design. There is no horizontal variation. Or in other words, there is no, the spy value is independent from the Trojan values. So this is nice and well, but we want to have a benchmark. So we want to have something portable that you can use on different chips, on different ISAs, it's possible, simulation or real executions. And for that, we follow the mbench model. So we have chip and board specific programs and functions that can be called from the benchmark, which is itself independent from the architecture. And we will abuse the tools that C offer, in particular volatile keywords and alignment attributes, in order to remove the noise from the measurements. But for now, it's only tested on our own RISC-V cores, because these tools has been built in order to verify all core designs that we are building, cores resisting timing leakages. So how do we do the BTSpy function, for example, in C? So basically, you see that we are aligning the function with respect to the cache line. This is because we want to avoid interference from the fetch of your processor. Then you select the branch from the input value O. Next, you use this value with a volatile dummy variable in order to force the computation of the address before the read time. If not, the compiler will compute the address just in time, but between the start and end. Once you have done that, you can now do your branch between the start and the end and measure the result. So are our benchmarks usable yet? For now, we have 4 benchmarks for L1 data cache, L1 instruction cache, branch target buffer, and branch history table. But we need more for return address stack or pattern history table, for example. We need to port to other chips. We don't have a multi-art story yet, and it's interesting things to do. So we have some preliminary tests for cross-art L1D, and pocket retention. So unfortunately, the documentation is not complete. We're working on that. And we need 2 important things. First, to deal with non-determinism. So in our settings, all measurements are deterministic. So we don't need to repeat a measurement. But in real cases, with an operating systems, it won't be so simple. And we need a nice metric. And I want to finish with these points. So visualizing the timing dependency is fun, but not very scientific. What we need is a timing metric that can say the amount of leakage. So what we want is the bits of transmitted information per unit of time. For that, we need to build the channel matrix from the timing matrix. So we want the probability matrix that the spy read O when the Trojan sends I. And for that, we need a decision criteria. From the timing, what does the spy decide is the value sent by the Trojans? And for that, we need to deal with non-determinism. From the channel matrix, we are usually computing the mutual information, but it can only demonstrate it there is no leakage, but it is useless as a metric. It won't give you relevant information of the degree of your leakages. For that, we need the channel capacity, which is hard to compute in a general settings, but it can be approximated. So as a conclusion, so we are proposing a benchmark suite in order to test easily common timing leakages source. It still misses some features like non-determinism, multi-art, and metrics. But I'm presenting the work now because I want your feedback on this tool. How would you use it? And so basically tell me a bit about your needs. So thank you.